In Chapter 6, Part 2, the Bohr Model and de Broglie, we're going to really discuss what do we know about light and what does that mean? So we're going to talk about line spectra, but before we do that, let's talk about light a little bit more. So we're going to have a light bulb, the filament inside, and so it's a light, so we'll color that yellow just so that we remember that that's a light bulb. And so when light comes out of a light bulb, look at your ceiling, look at your computer, light comes out in all 360 degrees. If you would like light to be ordered, you're going to pass it through a slit. This is an organizer. So you can kind of think about it that maybe the light's coming in this way or this way, but only the light that goes through, it will all come orderly through. This is somewhat similar to like a turnstile if you go to a Jags game or any other NFL football game. And so the slit organizer is going to organize everything. Then we're going to pass the light through something called a prism. And so this prism is going to give us a rainbow. And so we see this if you have a prism sitting on your counter. There are lots of pictures about this. So if we have this happening, this comes from what we're going to call white light. And so white light is the light that's in the majority of our light bulbs or light that comes from the sun. And so in white light, this contains all wavelengths of light. Now, in some cases, we can get a really specific wavelength of light. So there are some LEDs that only do a specific type of light. And so in that case, it might not be white light, but it might be blue light, and that blue light will do something similar. So if we set this up and we generate the light in a different way. So in this case, we're going to generate the light. Instead of using a white light, we're going to do the same thing down here, but we're going to use maybe a helium lamp or a hydrogen lamp. And so we get some light and it goes through an organizer, and then it's going to go through a prism. But in this case, we're going to get some specific lights where maybe you get only a couple of bands, and those bands are separated and not at all the same. So if we look at this light spectra, so this one up here at the top, this is hydrogen. We see a series of lines. And so these lines are, in different colors. But if instead we use a neon light, like a neon sign that you might encounter at anywhere with fluorescent lighting, what we see is a variety of different lights. But what you'll notice is that the lights might be similar, but they're not the same. So even in the case, let's not draw over it. But in this case, none of these lines are going to be the same. And so the question is, where do these lines come from? Why aren't they the same? And what does it mean that they're not the same? So hydrogen only has 4 lines, as we saw in the previous slide. And so what we see is that they are 410, 434, 486, and whoa, that's not really to scale. So we're going to erase this edge off. Extend this out much, much longer and give ourselves a 656 line. And those are all in nanometers. So the question was, how do these fit together? So Rydberg determined that the lines for the hydrogen spectra fit together using this equation, where 1 over the wavelength, so this is our wavelength, in meter, is equal to the Rydberg constant, which you can see here, multiplied by 1 over n1 squared minus 1 over n2 squared. So what this is saying is that the whole number integer n, where n2 is always greater than n1. So instances of that where n2 would be 3 equals n2 and 1 equals n1. So this tells us that we're going to transition from 3 to 1. And so as we move forward, we're going to see some other equations that feel like they should all be the same. But the Rydberg equation only works for emission. So it only works when we observe a line pattern. It cannot work for absorption or excitation, which we'll learn about coming together. But the Rydberg equation is starting to tell us about things that move around in elements that are different from hydrogen to helium and to neon. So around this time, Niels Bohr comes up with a model. So he wondered if these lines arise from electrons. If you remember back in chapter 2, we discovered the electrons and then kind of left the atom alone. So we're going to discover the orbitals where the electrons live in any given element. So Bohr couldn't quite figure out why the electrons don't spiral into the nucleus due to charge-charge attraction. So if you remember, we have a positive center and we have some negative particles just kind of hanging around. So Bohr suggests a new model. So he says electrons in an atom can only occupy certain orbits corresponding to certain energies. Electrons in these orbits have specific allowed energies. These energies will not be radiated from the atom. An energy is only absorbed or emitted in such a way to move an electron from one allowed state to another. So what does this mean? Like, we're going to talk a lot about it with electrons, but what does that actually mean? So if this is a stair step, and so if we have, in this case, I'm going to draw a person. I am not an artist, but you can either be on the first floor or you can be on the fourth floor, but there's not really a place where you could be here in the middle, or at least not necessarily. So what we are saying is that there are discrete levels. So you could be here, here, but energy is only absorbed or emitted. So in this case, we ignore the fact that people walk and they basically hop or are transitioned up to different states. So you can move from, let's just call this 1 to 2. You could also move all the way up here in a single move. So what we're saying is that the energy is going to move our person or our electron from one state to another, but we don't end up in half states. So you either make it to the next level or you fall back to where you came from. So Bohr uses his postulates and the Rydberg equation that the energy for the lines in the hydrogen atom are the energy equals negative h c RH 1 over n squared, to where this is Planck's constant. We have the speed of light, and we have the Rydberg. And those three things are all constants, and so realistically you could rewrite this as the energy is equal to negative 2.18 times 10 to the negative 18, 1 over n squared. So as he starts to think about this, he can calculate the energy of any given state for the hydrogen atom. So he starts making a diagram that looks kind of like this. Where we start at the different states. So we know, or we're going to come to learn, that the energy starts at n equals 1, and we know that n is a whole number. So if n equals 1 in this equation, we're going to get, I'm going to leave these as the values, negative HCRH is our value. And so one of the things he also noticed is that the states kind of work out in this pattern where they get further and further and further, or I'm sorry, closer and closer together. Whoa, that one's a little far. As they increase. And so as he looked at this equation, he started to realize that it would look at negative 1/4 HCRH, n equals 3, (1/9) HCRH. So he could calculate the energy for all of these. And so if you arise at n equals infinity, the electron leaves the atom. And so in this case, the electron can move between these states. And so what we're going to come to see is the electron can move in this direction, or it can move in this direction. And so what they were able to figure out using the Rydberg equation is that n is a whole number. And an electron can travel between two states using this equation. So the energy for an electron to travel between states it has to come from somewhere. So it's going to come from a photon. If you would like your electron to go up, a photon will come in and hit the electron, exciting it up to a new state. And then as the electron decays back to a lower state, it's going to give off an electron. So we can absorb an electron to go up in state, where NF is greater than N1. You can emit an electron to go down in state, where NF is less than Ni. So as we start to think about this in terms of energy, when delta E is positive, NF is greater than Ni. When delta E is negative, NF is less than Ni. So we can absorb an electron. We should have positive. When we emit an electron, we're going to lose energy. And so we can start to look at this and we can think about a few other things. If delta E is greater than 0, the electron absorbs a photon with E photon equals to H nu equals delta E. If delta E is less than 0, the electron emits energy as a photon with E photon still equals H nu, but that is equal to negative delta E. So in this case, this is going to allow us to kind of make this transition, and it's going to be really important as we think about electrons moving from state to state. So on your slides, you'll probably see a slightly different question, but it should read, an electron completes the transitions shown on the right. What is the wavelength of light emitted? So the first thing we kind of want to do is think about, okay, well, what do we know? We know that the electron, so NF is going to be 1, and I can just count up equals 3. So in this case, we're going to be able to calculate the change in energy. So we know that delta E is negative 2.18 times 10 to the negative 18, 1 over NF squared minus 1 over NI squared. So we can plug in our states. Negative 2.18 times 10 to the negative 18, 1 over 1 squared minus 1 over 3 squared. So when we plug this into our calculator, we get negative 1.94 times 10 to the negative 18 joules. And this equals delta E. So we know that this electron is emitted, and so the change in energy is equal to negative E photon, which is equal to H nu. So in this case, we know that the sign of this is going to change, and not just to make it go away. This is an important statement. And so we're asked to provide the wavelength of light. And so we're going to use the C equals lambda nu equation to plug in for this, to where delta E equals negative E photon, which equals hc over lambda. Oops, let's make that a real sign. So now we can start to rearrange this even further to give us lambda equals hc over delta E, or negative delta E in this case. So when we start to plug this in, it's 6.626 times 10 to the negative 34th joule seconds times 2.998 times 10 to the 8th meters per second, divided by negative 1.94 times 10 to the negative 18, or 10 to the 18, negative 18 joules. And when you plug this into your calculator, you should get 1.02 times 10 to the negative 7 meters. 1.02 times 10 to the negative 7 meters. In 1 meter, there's 1 times 10 to the 9th nanometers. And so that gives us 102 nanometers. So this equation feels like it's a lot of work in these types of questions. But what we can do is, it's rather simple. It's about moving these numbers around. And we've talked about calculating speed of light, or using that, and calculating E photon as well. So the Bohr model is really great, and it was really a big advancement in the field of where do the electrons live. But the problem is, it only works for the hydrogen atom. So it only works when there is one electron. So we were able to calculate how does one electron move back and forth. One up, one down, but there are never more than one electrons. So all of the other elements in the periodic table don't really apply. But what we learned is electrons exist in discrete levels. And we learned that energy is involved in the transition from one state to another. So we now learned that this is going to give us allowable transitions. And hopefully we're going to be able to convert this into information that applies to not just hydrogen. So around the same time, Louis de Broglie, who you can see in this picture, makes a wild suggestion that all matter, all particle matter, could also behave as a wave too. And so that for most items, the wavelength is so long that we can't see it. So what does this mean? When a football quarterback chucks the football, it has a wavelength, but likely that wavelength is so long you couldn't ever see it. So if we remember that the wavelength is watching a peak-to-peak transition, if in terms of a football pass, we only see the pass go from here, you'll never actually see this. So what we're trying to say is that all matter is going to have a wavelength. And so electrons behave as a particle in a wave. And so this was discovered in lots of different ways using a couple of different experiments. The double slit experiments, the single slit experiments, where they were able to determine it could be both a particle and a wave. And so this is de Broglie's equation, where Planck's constant, and this is the mass in kilograms times the velocity. And so in this case, this is going to give you the wavelength. And so this does work, but we don't talk about it a lot here in Gen Chem 1. But I think it's an important statement that electrons can behave as a particle and a wave. And so a few years later, we start to discover some of the issues with thinking about the electrons as a particle and a wave. So for an electron, it's really small. And so we can either know where it's going or how fast it's going. And so this is the change in position. or the momentum. And so these deltas in front of it basically say either how fast is it going, plus or minus, or what is the change in which it gets there, is going to be greater than or equal to Planck's constant divided by 4 pi. So the thing is, for electrons, we can either know where the electron is, or we can know how fast it's going. We can't really know both. And so this is the Heisenberg uncertainty principle. A lot of times people talk about, is the cat, like Schrodinger's cat. So this is all involved in there. And so what we're going to learn in the next 2 videos is where are the electrons? And so now we can kind of get an idea of where they could be. Or we can look in the past and see where they were. But it is really, really hard to say the electron is exactly right here at this time.